So, the topic at hand, what makes small fields so challenging? Number one, of course, size. It goes without saying, but we do have to talk about it. It is the size that makes it tricky. There are some other pieces that fall into that contribute because of that. Source occlusion, changes in energy of the beams, how the penumbra is shaped, the differences between that and large fields, loss of lateral charge particle equilibrium. Most of what I'm talking about in terms of the physics of this or the concepts that we need to think about come from a couple of publications. One is this IPEM report number 103, small field megavoltage photon dosimetry. And the other is the joint publication from the AAPM and the IAEA on dosimetry of small static fields used in external beam radiotherapy. So that's TRS 483. So what is a small field? We're talking about these small field conditions, and TRS 483 defines small fields as having at least one of these conditions, either loss of lateral CPE on the beam axis, or partial occlusion of the primary photon source by those collimating devices, again on the beam axis, or the size of your detector is similar to or large compared to your beam dimensions. And that's usually the one that is the easiest to know about, but also the one that sometimes jumps up on people, surprises them, especially if you're really trying to measure those very small fields. Your detector is nearly the size of your field, and that makes a very large difference in the corrections that are required. So going through those points that I listed at the beginning, I'm just going to go into a little more detail on them. The physical size of these fields is usually in the range of 4 millimeters to 40 millimeters, again, depending on the energy of the beam and the detector that you're using. Something to think about is, how are you defining your field size? Are you defining that based on the jaws, or is it based on a full width half max from a stereotactic cone, for instance? The shape of the field, the difference between where those jaw positions are or that collimating device and the actual full width half max of your field, that discrepancy increases as your field size decreases. You get decreased output, as you can see by the peak of the curve here, as you go to smaller fields. And the other thing to be considering is that alignment of your detector based on your field size also becomes more important as your field size gets smaller, because a very small geometric misalignment can translate into a very large, both geometric and dosimetric error in your measurement. Source occlusion refers to when this collimation system becomes small enough that you're actually blocking the primary fluence from this the beam source where the electron beam hits the target, or a scattering source for electrons. Usually this is photons though, for small fields. That's what we're referring to here. Again, the IPEM report 103 does an excellent job of discussing this. Lateral charge particle equilibrium was the third thing on that list. Your equilibrium condition is the lateral scattering distance has to be equal to or greater than the range of the electrons in your beam. So the practical translation of that is that you'll likely start losing lateral CPE when the beam width goes down to less than 2 times your Dmax distance. So what that really means is that your higher energies lose that plateau region, that flat, nice equilibrated region, sooner than the lower energies, because your electrons have so much more energy, need to travel farther, and therefore scatter out more easily as you get to those smaller fields. So your detector positioning, the perturbation corrections, all of that comes into play sooner for higher energies as you're going smaller and smaller in beam size. So it is also, as we see in some of these profiles, it's also very important to understand the profiles of your beam and not just output factors, because the shape of that beam affects your volume averaging, affects your lateral charge particle equilibrium, and therefore affects your measurements. So how do detectors themselves impact the measurement? Those first conditions are really about the beam itself and the shape of your beam and the size of your beam. But the detectors themselves also impact your measurements. So the first thing to consider is your detector size and the shape of your detector. So the size and shape, of course, affects the volume averaging. So how much of the profile or the beam shape are you averaging over the active region of your chamber or your other detector? We talk about spot size for detectors. This really indicates the region where you are replacing phantom material with detector material. It's kind of a representation of that active region of the detector itself. The detector size and shape then also impacts how accurately you can determine the beam penumbra, again, because of the volume averaging, because of the distance over which you are integrating the signal. So consistent and accurate positioning is very important. If you're using film, it's good to understand that for very small fields, sometimes the scatter within your scanner can affect the resolution that you can get in the very small center portions of your field. This plot on the right is from an older publication from Meltzner and de Word about gamma knife output factors. And the solid line here represents the active region of the detector. But if you look at the buildup required on each side of the detector, so walls of the detector as well as a little bit of buildup, this is why we talk about spot size. But needing that equilibrium on each side, your volume side, you actually, for this gamma knife, you lose your lateral charge particle equilibrium sooner on the 8mm helmet, even though it looks like your detector fits within the flat region of that field. So they did see an impact on the output factors based on that overall size of the chamber plus buildup. Second way that detectors impact your measurement is perturbation of your beam. So you're changing the density of the material right there at the point of measurement. So you're perturbing your fluence, which of course affects your dose, alters dose by replacing water with the detector, and that has to be corrected for. So depending on the detector type that you're using, some of the questions that you would want to ask about your detector, how big is your air cavity? What is the density of your diode? For diodes, are they compensated diodes or not? Some diodes have either an air gap to try and offset the density of the diode itself, or some other type of compensation to attempt to make it more water equivalent. However, this can actually alter the response at other energies in a non-desirable way. So how does that response vary with energy for a diode, whether it's compensated or not? There are sometimes published corrections available for your detectors. Sometimes you have to do more of a daisy chain on your own. The tricky part with using published corrections, it is, I agree, very nice to use published corrections because they have been peer reviewed. They are out there for public use, but you have to match the conditions under which they were generated, or they may not apply to your measurements. So here's an example, I guess, of some publications for various set of diodes as well as ion chambers, showing differences in perturbation as you change the depth, I believe. Third way that detectors impact measurement is your signal level. So ion chambers have a signal that is proportional to the collecting volume, which means that as you decrease the volume, your signal level decreases as well, regardless of the actual output of your machine. So your signal to noise ratio becomes much more of a concern, and very small signals also require a very sensitive electrometer, an accurate electrometer for measuring those extremely small currents. Diodes have the advantage of generating a larger signal than you would get from a microionization chamber. However, they have, of course, the trade-offs of the increased density and the potential energy dependencies of those detectors as well. If you're considering that signal to noise ratio for these small signals from something like an ion chamber, it's important to make sure that you've allowed your electrometer to warm up fully. Sometimes that means just leaving it plugged in overnight so you don't have to worry about it. Make sure you check the leakage on your electrometer or even on your electrometer with the cable to make sure that you aren't causing yourself some heartache by trying to overcome a leakage that is comparable to the signal that you might be measuring with your ion chamber, or big enough to affect it anyway. You also need to ensure that you're matching the signal level that you're measuring with the proper electrometer range. I can't tell you how many times I've talked to people who say they have issues with small field measurements, and it turns out that they're using their electrometer in a high range. It's very important to ensure that you've matched the capabilities of your electrometer with the detector that you've chosen. You can also have some effects from your triax cable, both the cable on the chamber and potentially the extension cables. If you have a tightly wound extension cable that you lay out through the maze and into the accelerator vault, it can take several hours for the physical relaxation of the materials within that cable, and that can cause some triboelectric effects, so kind of a low-level leakage current that can affect small field measurements. So if you try and zero your system and it keeps drifting, consider your cable. Consider winding it more loosely, laying it out beforehand, maybe off to the side, so that you can overcome that particular relaxation problem as well. You can also induce a signal in your measurement if you're irradiating some of the cable through Compton effects on that center wire. So it's good to make sure that you don't have any more cable in the field than you need to, just to ensure that you aren't going to have to deal with much of that. Accuracy of your detector then also affects measurements. Do they have any energy dependencies? Diodes sometimes can show a low response out of the field for the lower energy scatter, which can result in an underestimation of low dose regions in your stereotactic patients. We talked about compensated diodes. They can be good or they can be a little frustrating depending if you're using them in the configuration which they were designed for, and if that's something that you're looking for in your diode. Corrections for a detector that has energy dependencies become depth dependent. So as you go deeper in your measurement for a percent depth dose, your spectrum is changing, and depending on just how sensitive your detector is to those changes, you may have corrections that have to be applied at different depths. Changes in scatter conditions are similar, just because you have the low energy scatter, the presence or absence of it can affect the overall result of your detector. If your detector has any angular dependence, it's best to use it in the orientation for which it was designed. Otherwise, you do need to be aware of implications of using things at other orientations and potentially applying corrections for that as well. And does your detector have dose rate or dose per pulse dependencies? This requires understanding both the way your accelerator functions. If you increase the dose rate, does it just increase the number of pulses, or is it actually increasing the magnitude of the pulse, so the dose per pulse? Most of the accelerators simply add pulses, but there is some dose per pulse dependencies that can come in. And as we start branching out into these ultra high dose rates, then dose per pulse actually becomes a huge factor, as I'm sure anyone in the flash world has encountered, etc. There's other things about your detectors. I've talked about ion chambers and diodes and just briefly mentioned film, but there are other things like radiochromic gels, TLDs, OSLDs, that sort of thing. You need to consider the leakage, if there's any drift in your detectors, timing of readout for some of those, repeatability, how consistent are these detectors, what resolution do they have, is it fine enough to measure the field sizes that we're looking at, can it be calibrated or does it have to be daisy chained to something else, or is it just a relative type detector? All of those things come into play as you're picking detectors. So what is a poor physicist to do? It is tough doing small field measurements here. Sometimes it feels a little bit like ticking time bomb. If your physician has said, we want to treat SBRT lung, I have some small tumors I want to treat, and suddenly you're tasked with ensuring that the dosimetry is accurate. Well, I think I can help you. We do have some options here at Standard Imaging for megavoltage beams. One that I'll talk about first is the established technology, but with known perturbation issues. Those would be the diodes, D1H and the D1V. The newer technology, I know the scintillators have been out for a little while, but they are new to a lot of people. So that's the W1 and the W2 plastic scintillation detectors. And then I'll talk about an old standard, an ion chamber, finally working properly in miniature form. Again, the A26 has been out for a number of years now, but it does take time for word to spread about the construction, the accuracy of these sorts of chambers. So every detector that you'll find, whether from Standard Imaging or from somewhere else, has both strengths and limitations. And so your best solution really is a good combination of detectors. So the diodes, the Standard Imaging diodes are the D1V and the D1H. It's the same diode, but in different housing, so it's in two different orientations. The vertical one is intended for scanning so that you have minimal perturbation of the water surface as you're moving that around. And the horizontal one is a little bit nicer for a slab phantom to be able to mill it out, to fit the diode in, or to be able to do surface measurements. It's an unshielded diode with a 1 millimeter diameter spot size, and there are a few publications that show correction factors for those diodes. There were two in 2014 in particular that looked at both measured and calculated factors. This plots from one from Papakonstantopoulos et al. In PMB, and you can see the D1V here in green compared to field size for the beams they were measuring. Another publication, this was in one of my earlier slides from Paulo, the publication is from Paulo Francescan, but shows the D1V here in the green plot. I will point out that the scintillator here is the red near one for the whole time. The advantages of the diodes are that the diodes are a very well-established technology. It's something that we as physicists are comfortable using. We kind of understand some of the dose degradation. We know that we need to watch out for energy dependencies. But they are nice to use for scanning because you get a nice high signal and can get a small resolution on your measurement, volume integration, the spot size of the measurement. That's the minimal volume averaging part, I guess, as I'm looking back at my bullets. They have a little bit of angular dependence, especially as you get far away from that normal orientation, but it is low angular dependence for those. Limitations of diodes are pretty standard for diodes. They're not water equivalent because they are diodes. They're at a higher density, so they do require those corrections. And the fact that there is some angular dependence is a limitation. The second set of detectors I would offer are the scintillators. We have two configurations of that. The first generation device is called the W1. It has a 1 millimeter diameter, 3 millimeter long organic scintillating material. The second gen device has multiple fibers. You can use either the 1x3 that matches the original W1 detector, or we make a smaller one that has a 1x1 millimeter active region. The primary advantage of the scintillators is that this material is water equivalent for megavoltage photons and electrons. And therefore, you don't have to worry so much about those spectral changes as you get occlusion of the primary source or depth corrections or just changing between a 6 MV versus a 6 FFF versus an 18 MV, any of those. The water equivalency means that your response is, it really means that you're not perturbing the dose right there at the point of measurement, and all of the correction factors that go with that perturbation are eliminated. You do, though, require a new correction because we're looking at optical light. The high energy electrons generate Cherenkov light in the optical transfer fiber. So it manifests as a stem effect. You get increased signal from the Cherenkov light as you have increased amount of fiber in the field. And so there's a method that we have built into our Supermax for use with the W1 or the Max SD, which is the dedicated system for the W2, to be able to walk you through the characterization of the fiber so that you can correct for that Cherenkov light. This is also not a calibratable detector that you can send off to the calibration lab and have it come back with a cal factor that's good for 3 years. It's a material that degrades as it's dosed. I'm sure all of you have seen old PMMA phantoms, the clear plastic phantoms that have turned yellow as they've received dose. The same thing happens with our optical transfer fiber. That fiber optic yellows as it receives dose, which then changes the spectrum of the light that's transmitted through it and attenuates more of the light that's transmitted. So it affects the output, and you do have to recalibrate periodically as the material accumulates dose. We get about a 2% decrease in signal for every kilogray of dose to the fiber. So it's a slow degradation. It's not super fast, but it is present. The method that we use for the Cherenkov correction is a 2-channel chromatic correction. I apparently forgot to put the publication up here, but it's from Matthew Bouillot et al. In medical physics that defines this 2-channel chromatic correction. And in essence, we're splitting the light into 2 sections, what we call the blue portion of the spectrum and one we call the green portion. So our scintillator is a blue scintillator, so it's centered in this blue region that we're analyzing. Cherenkov light is a broad spectrum light, so it is actually heavier in the blue section than the green. But the nice part here is that when we split the spectrum, this one is primarily signal from your scintillator, and the green portion is primarily Cherenkov. So if you do 2 sets of measurements, keeping the dose to the scintillator tip, the active region of the scintillator, constant, and changing the amount of optical fiber that's irradiated, then only the Cherenkov contribution changes in both of these channels. So we look at the difference in the blue channel between what we call a maximum fiber configuration, that's the large amount of fiber in the field, and a minimum fiber configuration where you have the fiber coming straight out of the field. And the difference, the ratio of the difference in the blue channel to the difference in the green channel can be used as a correction factor. We call it the Cherenkov light ratio. And with this Cherenkov light ratio, you can correct subsequent measurements using the amount of signal in the green channel times the Cherenkov light ratio to subtract the Cherenkov from the blue channel. And that gets you the scintillator signal alone. The 2 holders we have for it are shown kind of schematically down here. There's a slab phantom that fits in a 20 by 20 field that is, 30 by 30 field that is provided with the W1. So you can, there's a milled out channel for the minimum fiber configuration and a channel for the maximum fiber configuration where the fiber is wrapped around, as well as some alignment marks for a 10 by 10 field for a dose calibration. If you choose to do a dose calibration, that's really just a scaling factor that's applied here to convert from the nanocoulombs signal that's measured, or picocoulombs, depending on your signal level, to centigrade. The blue bracket here is provided with the W2, so you can do these same sorts of measurements in a water tank, and this entire thing fits within a 10 by 10 field. So you can do the characterization in a smaller field that way as well. If you do a dose calibration, really it just requires you to give that tip of the fiber a known dose. So usually in your reference field, whether that's a 10 by 10 for your linear accelerator or a 6 centimeter cone for your CyberKnife, that's where you would do your dose calibration. Similar to a daisy chain. So with the W1, I mentioned it's the 1 millimeter diameter, 3 millimeter long scintillator. There are numerous publications about the W1, but one of my favorites, as we've been talking about this whole time, is TRS 483. So in all of the tables where the W1 is listed, every one of these correction factors is unity. So that's really the assurance that yes, this truly is water equivalent, and you don't need to worry about these corrections that other detectors need down at these small fields. So strengths of the W1 are that KQ value of 1, as reported in TRS 483, that really demonstrates the water equivalence for megavoltage, photons, and electrons. It does not show dose rate or energy dependencies, and it has a negligible temperature dependence. It's about 0.1% per degree Celsius, if I recall. All of the measurements that we have been performing are at room temperature, so a slight difference in room temperature does not affect your measurement. You don't need to correct for it. If at some point we start doing on patient surface sort of measurements, which we are not FDA cleared for right now, but if we go down that road in the future, then there may be some temperature corrections that would need to be considered. Limitations of the W1 are that it was not designed for scanning or for large fields. This was a first generation device and was designed for point measurements only. So it works with a 2-channel electrometer like our Supermax in order to do that 2-color correction for the Cherenkov light. It is a low signal device, so it has a low signal to noise ratio as well. There's a higher uncertainty for out of field measurements with the W1 in the low dose region. It does require the characterization, calibration if you want to give it a reference dose in order to tie the measurement output back to dose. And occasional recalibration as it accumulates dose to the fiber and that signal decreases. The other thing I put here as a limitation is that there's a learning curve with scintillators. Optical signal measurements are non-intuitive to many users. It doesn't function exactly the same way as your ion chamber, and so it takes a little while to be comfortable and confident in using this detector. So I would recommend, if you get a scintillator, plan in some time for practice with it, for getting used to it, for becoming confident in how you use it and what your measurements should look like. For the W2, we were able to improve the optics, the sensitivity of our optics, and so we could decrease the size of the active scintillator. We kept the option for a 1 by 3 millimeter fiber because there were so many publications about the W1, and to have that geometric an identical fiber. They're made the same way. They're all made first and then earmarked W1 versus W2 afterwards, depending on what we need. So having that link, as well as having an option that gives you a higher signal for potentially for faster scanning or better signal to noise ratio for fields that a 3 millimeter integration is fine for. That's why those are both available. It does have a dedicated optics and electronics unit called the Max SD. That also helped us decrease the electronic noise of the system, which improves the signal to noise ratio. You can perform point dose measurements directly with that Max SD. It also allows you to walk through the Cherenkov correction and a dose calibration if you want to, right there with the device itself. But it also can perform a fast Cherenkov correction for every 10 millisecond integration from the optical fiber and convert that corrected signal into an analog current output that's sent then to a water tank electrometer, for instance, if you're doing small field scanning. So The way that looks, if you're scanning with the W2, you do need to do those characterization measurements beforehand. You do not need to do it every time you use it, but it is nice to have it out of the way before you're planning to do your longer set of measurements or cone characterization or something like that. The fiber has an adapter sleeve that's sent with it. I probably need to zoom in on this. Next time around, there's a little set screw here that will allow you to gently hold the scintillator in place, but the adapter sleeve allows it to be used with any standard chamber holder for any water tank that you might be using. That optical fiber is then plugged into the Max SD so that it can take in that optical signal and perform the Cherenkov correction. And then the corrected signal is output from the Max SD to your water tank scanning electrometer. This is our DoseView 3D system. But the idea here is really the Max SD is a pass-through, and the water tank electrometer doesn't have to know about it, doesn't know that there's anything going on there. To the water tank electrometer, it looks like you're scanning with a diode, because you don't apply bias to it, but anytime there's an irradiation, there's a signal received by the water tank electrometer. You do have to scan slowly. We recommend a point-by-point measurement of about a second at each dwell point, and really that's to allow the system to overcome some of the signal-to-noise limitations. We do apply a gain to the signal so that it's in the range that your water tank can measure, but to give you nice, smooth, reliable, repeatable data, it's good to scan slowly. If this were because this is a small field detector, it really is worth taking the extra time for your small fields to be able to get good scanning measurements. So with the W2, we've kept all the strengths of the W1. It's the exact same fiber, just with a smaller active region on the W2 1x1. And we've gotten rid of a couple of the limitations that the W1 had. There are a couple questions. Can this be measured for the beam profile, the W2? Yes, the W2 can be used to measure the beam profile. You're just looking at a 1 millimeter spot size, just like you would have with our diode for scanning. And for measuring the output correction factor for the W2, I had the equations back there on the other screen. Sorry about that. It's also delineated in the user manual if you wanted to do it on your own, but really you would measure the maximum fiber configuration, the minimum fiber configuration. The system will calculate a Cherenkov light ratio, or you can do it on your own in Excel if you want to double check it. And then if you want to do a dose calibration, then you give it a known dose, and it creates that conversion between the current that's measured and the dose that's measured in that known configuration, so that subsequent measurements can be converted into dose as well. And then if you were to use it for output factor measurements, for instance, it would apply that Cherenkov correction from the saved file that you have created within the system. Hopefully that answers the question. For micro-ionization chambers, I mentioned an old standard now working properly. The A26 is our newest micro-ionization chamber. It's been, oh goodness, it's been out for a number of years now. I can't remember the exact year that it was released. But there was some PhD work done by Dr. Jessica Miller at the University of Wisconsin-Madison, looking at the odd behavior of micro-ionization chambers that were available on the market at the time. Not just our chambers, everybody's chambers. And what was being seen was, in particular, a polarity ion recombination type effect. But when you changed the polarity, you often got very strange behavior from the micro-ionization chambers. And what Dr. Miller did was track down the source of that particular behavior, and it had to do with conductance and the shape of the electric field. But the A26 was designed as a result of the findings that she had reported in her thesis. So we designed this as a reference class ionization chamber for small fields to meet the definition of a reference class chamber from the IEC and from TG51. And as we were going through this design, there were several things that we had to consider. One was, of course, the chamber spot size. We made it spherical on purpose so that the orientation doesn't affect your volume averaging if you're turning the chamber about its about its center point of measurement. So if you were scanning, say, cross plane versus in plane, you wouldn't get differences in the averaging over the penumbra of the beam. We modeled the electric fields to make sure that we knew that shape and we knew the volume very precisely. The chamber volume is really as small as we can make it. This is the smallest well-behaved ion chamber that you will find. The A16 is slightly smaller. I know there's another smaller one out there on the market. They have a wire center electrode in the A16, which is what causes some of that different behavior from the A16 versus the A26. The A26 really is the best small chamber that you will find. The other thing we had to consider is whether the signal to noise ratio would be sufficient for the intended use. And yes, as long as you're using a good quality electrometer, those smaller signals are sufficient. So strengths of the A26 is that it is a reference class ionization chamber. Its spot size is independent of its orientation, so you don't get differences in volume averaging for different orientations of the detector. Ionization chambers are also very familiar technology for most physicists. People are comfortable with them. It's what we've been using for years. We understand the strengths and the limitations a little better than we do. And our expectations and troubleshooting for these is something that's fairly well established as well. Limitations for the A26 really is only that it requires corrections because it has air volume, because it's an ionization chamber. There is a change in the perturbation, right? Or there is a change in the fluence due to the perturbation of the air gap right there at the point of measurement, as happens with any ionization chamber. So what about small X-ray fields? We have a very small parallel plate ionization chamber for low energy X-rays or electronic brachytherapy sources, that sort of thing, superficial skin therapy. This chamber has a mini parallel plate here at the tip. It's got a just under 2 millimeter diameter collection region. And excellent energy response for those lower energy X-rays up to cobalt 60. I would be remiss if I didn't bring up our electrometers, especially after talking about the need for high quality electrometers. The two primary ones are the Max 4000 Plus, which is really the workhorse. It's a very robust, long-lived single channel reference class electrometer. With a good range and resolution for most of your measurements, pretty much all of your measurements. The Supermax is our high-end 2-channel electrometer. It does have a touch screen. It's very easy to use. Has 2 channels with independent bias. It's also very nice if you're using the W1 scintillator with it. It has a very fast 1-minute warm-up as well. A little bit higher resolution at the low end, as well as range. Particularly for those small field or small signal measurements. And both of these chambers have an industry-leading 5-year warranty. So we've been making them for a long time. We stand behind them all the way. So if you're looking for a new electrometer, these are excellent small field electrometers. So with that, sorry for keeping you so long. We can conquer small fields. I'd be happy to talk with you at a PM. Please stop by the booth. Or if you need more information, visit our website, standardimaging.com, or contact your sales representative at sales@standardimaging.com. Please ask any questions you've got. Let me know if you have anything you'd like clarified. Otherwise, thanks so much for your attention. I really do appreciate it. The question about the W2, is there angular dependence? Does the orientation of the detector matter? For the W2, there is a small amount of angular dependence that manifests only if you are irradiating right from the tip of the detector down the fiber. So, and that has to do primarily with the Cherenkov. Cherenkov has a preferential production angle of 45 degrees to the direction of travel of the electrons. And we are using the property of total internal reflection of the fiber to transmit the light down the optical fiber. And so the combination of these two things makes the Cherenkov spectrum slightly different, as well as higher at that end-on orientation. So we do recommend that you avoid that particular orientation if possible, only because there is a higher uncertainty in your Cherenkov correction at that orientation. The question of, can we use the A28 ion chamber for small field dose measurements? Yes, absolutely. The A28 is a scanning volume chamber, so it is a little bit larger than the A26, but the A28 was made right at that same time as the A26, and so it is every bit as good in terms of reference class quality as the A26. It's just slightly larger, so you're going to run into small field effects a little bit sooner than you will for the A26. A question about advantage and disadvantage of film in small fields. Film calibration is a little bit tricky when you get down to these small fields, primarily because some of the scanners, depending on how they collimate the light, if you have a very small irradiation, so a small dark dot on your radiochromic film, and you're trying to scan that profile, you can get scattered light around the dot, around that region, that can decrease the apparent density of the center of that very small region. I have run into this with very small brachytherapy source measurements when those are scanned. I don't know enough about it other than to caution you about that for very small fields, to be aware that that could be a problem for your scanner. And it's been long enough that I don't recall if there's a brand or style of scanner that works better, but it is something to be careful of with these very small pinpoint type exposures on film.